Hi everyone, I am Prenu Sumro. Me and my colleague Jing Chen are sending you greetings from Chalmers University, Sweden. We are PhD students in Department of Computer Science and Engineering. In this presentation, we'll present our joint work on scheduling task parallel applications in dynamically asymmetric environment. The plot of this talk is as follows. I'll start with the motivation and background, then proceed with the introduction of our scheduler. Jing will then walk us through the rest of the technical details of this work. Applications observe performance variability due to a variety of dynamic events, collectively called as interference. For example, I/O events, user activities, co-scheduled jobs, and OS power management, to name a few. As the scale of the system heterogeneity keeps increasing, tackling the interference becomes even larger concern. And it is particularly bad for parallel applications because of synchronization and resulting load imbalance. Common strategies to reduce interference include eliminating unnecessary activities at the system level. So, how about mitigating interference in task parallel runtimes? In this paper, we explore the opportunities at hand to address this problem. So, what is performance asymmetry? It occurs when individual cores have different progress rates, example MIPS, during execution. Applications are not directly aware of interference nor source of interference, rather they observe temporary episodes of performance asymmetry. Performance asymmetry sources are categorized into two. First, fixed asymmetry, which is hardware asymmetry like cores with different compute capabilities, for example ARM Big Little. These type of sources are permanent and does not evolve over time. Another category is dynamic asymmetry, which is execution time activities, for example DVFS for power management, sharing of resources between applications, or dynamic recompilation in some platforms, for example NVIDIA's Jetson TX2. In our paper, we address two scenarios of interference. First, DVFS activities and the co-scheduled applications. The proposed runtime uses some scheduling techniques to address the interference. First is moldability, which is flexibility to work as either single-threaded or multi-threaded task, and the knowledge of task criticality to handle the performance asymmetry. So the question becomes, how moldability and knowledge of task criticality can be leveraged to address interference? Let's talk a little bit about background so that we can better understand the concepts introduced in this work. The application model makes use of DAGs, which is directed acyclic graph, and it is a common way to express the multi-threaded applications. This figure shows an example of a DAG. We make use of high priority tasks, also called critical tasks, which are color coded as dark red in this figure. These tasks are the ones that release a large amount of dependent tasks or tasks that lie on the DAG's critical path. For example, in this figure, T0, T1, T5 and T9 are high priority tasks or critical tasks. The critical path is also T0, T1 all the way to T9. We make use of DAG parallelism, which is basically the total number of tasks divided by the length of critical path. In this figure, DAG parallelism is 4. We use task types to define different functions implemented as tasks. Another piece of information used is execution places, which is a tuple of leader core and resource width, where leader core is starting thread number and resource width are the number of cores. For example, the execution place for T0 could be 0, 2, which means the task is given a resource width of 2 and T0 is scheduled on core 0 and 1. We now proceed with the description of Dynamic Asymmetry Scheduler. The proposed scheduler is built on two key ideas. We leverage a performance modeling approach called Performance Trace Table (PTT) to detect, predict, and predict performance asymmetry on a per task level. The second idea is applying scheduling techniques to minimize the impact of interference. That is predicting the best possible execution place for high priority tasks according to PTT and molding the task to reduce inter-task contention and resource oversubscription caused by interference. We have two variants of Dynamic Asymmetry Scheduler. First is DAMC, which is a Dynamic Asymmetry Scheduler with moldability and targets parallel cost, which is the product of execution time and the number of cores. This variant basically targets to reduce parallel cost and minimize the resource usage, and it protects from overcommitting the fast cores in the heterogeneous platforms. The other variant is DAMP, which is Dynamic Asymmetric Scheduler with moldability. It targets the best performance with the knowledge of the critical task, where we basically perform a global search for critical tasks and select the execution place that minimizes the predicted execution time. Thanks for listening. I'll now ask Jing to proceed with the technical details.
Thanks for my colleague Pira's great presentation. Now I will introduce the rest sections. In order to implement the Dynamic Asymmetry Scheduler, we develop an online performance tracing model called Performance Trace Model, in brief, PTT. We implement PTT as a table, and here is an example of 4 cores. It aims to predict the execution time for future tasks given a set of resources. Each entry is an elastic execution place tuple. The first dimension is leader core. The second dimension is valid resource width. As we can see here, the valid resource width we set here are all possible divisors of total number of cores. So the table size is the number of cores multiplied by the number of valid resource width. At the very beginning, all entries are initialized to 0 to make sure all entries will be visited at least once. After a task finishes execution, the leader core is responsible to update the corresponding entry, and the updating method we use is a weighted ratio 1:4. That means after roughly 5 times updates, PTT will fully adapt to the performance change. And for each task type, only one PTT is needed. Then we introduce how PTT is used for different priority tasks. High priority tasks globally search all possible entries of PTT to get a best one. For different schedulers, the minimizing target is different, either for parallel cost or execution time. Well, for low priority tasks, we do a local search. It means that we keep the launching cores fixed and only search for the best resource width. In this case, we keep reducing the data locality. And for the local priority tasks, they target for parallel cost whatever DAMP or DAMC. This figure shows the task scheduling flow chart. It combines the different priorities and different targets. For low priority, local search. High priority, global search. Then it depends on DAMC and DAMP. PTT has several advantages. Firstly, it is aware of interference activities by dynamically updating the execution time in the table. Secondly, it only requires few information, like the number of cores and core cluster organization. And this information can be easily obtained by HWLock. Thirdly, those update happens during the execution time, which is different from profiling phase. Because in profiling phase, users need to model performance before execution, which costs more overhead. And our model is independent of platforms suitable for both asymmetry and symmetry platforms. Also, we measure the PTT visiting overhead on a 6th platform called Text2, which I will introduce in next 2 slides. It turns out that the overhead only occupies the 0.2 to 0.5% of whole application execution time. But PDD has one limitation. When using the PDD on very large system, it may require more space, which means poor scalability, and this problem will be solved in our future work. The fifth section is experimental setup. We use two platforms for our experiments. First one is NVIDIA Jetson TX2, which is an asymmetric platform. It has two clusters, Denver and A57. Denver is generally powerful and faster than A57. The other platform is a symmetric platform we call it Intel Haswell node. It has 20 cores in total and 2 sockets. For benchmarks, we use synthetic benchmarks and two real applications in order to build the synthetic DAX and also represent different task tab. We use 3 kernels matrix multiplication, copy, and stencil. The applications include k-means clustering and two-dimension height. Then we evaluate several scheduling policies. So first one, random walk stealing. It is a greedy scheduler and it is not aware of call asymmetry. It's random walk stealing plus modability. We add modability based on random walk stealing, and here PTT is used to search for the best resource width for each task. The second main scheduler is fixed asymmetry scheduler. It knows the call asymmetry before execution and task criticality. Critical tasks go to the fast cores and cannot be stolen. Its variant, fixed asymmetry plus modability, adds the modability by using the PTT. Then, Dynamic Asymmetry Scheduler series. DA is without task modability and keeping the original citing resource with 1. Only using the PTT to search for the fastest core for critical tasks and best resource width for the non-critical tasks. DAMC and DAMP we have introduced before. All the schedulers are implemented based on the CTOL runtime, and here we provide a GitHub link in the footnote. Evaluation results. Firstly, we test how those schedulers react of co-running interference applications, and here is an experiment. It's conducted on TX2. The co-running background application is matrix multiplication on one Denver core, which is expressed as C01. This figure shows a throughput comparison on different DAG parallelism. Y-axis is the task per second, so higher is better. When adding the modability to random walk stealing, it improves the performance, while for fixed asymmetry, it seems like no obvious change. The last 3 bars are Dynamic Asymmetry Scheduler, and we can see they perform better than the other 2 kinds of schedulers. For example, the DAMC achieves up to 3.5 times speed up than random walk stealing, and compared to fixed asymmetry plus modability, it achieves up to 90% and 85%. So in order to figure out why dynamic asymmetry achieves better results, we do a further step to analyze execution places of priority tasks in each case. Still, we analyze the synthetic matrix multiplication with parallelism 2, which means 50% of tasks are priority tasks. And this is random walk stealing result. The interference is running on C01. Leader core C0, resource width is 1. The faster Denver cluster includes 3 configurations, C01, C11, and C02. As we can see that 14% in one random walk stealing is queued here. And for random walk stealing plus modability is 8.2%, which is 3.7% plus 4.5%. While in fixed asymmetry and plus modability, the percentage is much improved. All priority tasks execute on faster Denver core, but for fixed asymmetry, it is not aware of interference, since half-half on each core. In the fixed asymmetry plus modability, C11 execute 13% more tasks than interference core. That's because interference core C01 executes so slow. Then the C11 will execute more tasks. Dynamic asymmetry results are promising. As we can see, interference core only execute less than 2% of priority tasks. The other faster Denver core takes over 98% in day A. In DEM-C, since C02 also includes this interference core, so only 1.3% are executed with the two cores. In DEM-P, when targeting performance, also 4% tasks are executing on 4 A57 cores. Because sometimes using 4 A57 cores is faster than using the 2 Denver cores, since interference activity is acting here. In summary, dynamic asymmetry schedulers have fewer priority tasks executed on the interference core, and it achieves better interference awareness and high performance. The other type of interference is DVFS. Here the figure is stencil on TX2. We monitor DVFS as a core-screened periodic frequency change from maximum to minimum to maximum again. For each setting state for 5 seconds, we could see that random walk stealing and fixed asymmetry, they show the linear trend when the dark parallelism increases. While for dynamic asymmetry achieves higher throughput even in the low parallelism, we can see that from parallelism 3, the performance of dynamic asymmetry scheduler are almost the same. And also, they are more resilient to DVFS interference. Here we can see that DEM-P is much better than DEM-C in parallelism 2. This is because when Denver cluster changes to the lowest frequency, DEM-P will turn to executing tasks using 4 A57 cores. While the DEM-C target for parallel cost will use less A57 cores than DEM-P, then in this case, DEM-P will execute much faster than it will achieve higher throughput. Because of the time limit, we cannot present more interesting results of these two applications. If you are interested, please go through our paper. Finally, conclusion. Firstly, our experiment indicates that random walk stealing and fixed asymmetry cannot effectively aware of system dynamic change interference. Secondly, the PTD is developed as an online dynamic performance tracing model on per-task basis, and the result shows it achieved better interference awareness by tapping two types of interference, DVFS and co-running background activities. Thirdly, we compare the schedulers with or without task modability, and we can see that task modability sometimes makes the scheduler more resilient to interference awareness. That's all. Thanks for listening.